Hello class, welcome to the next segment in lecture 10, and in this segment we're going to tie everything together to see what Newton's second law and our equations of motion actually look like in our newly defined natural coordinate system. So with that, let's go ahead and dive right into it. So you may recall from lecture 1 that Newton's second law is, one way to define that is the change in velocity of an object is equal to the sum of all the mass normalized forces, which if we tie that into our natural coordinate system gives us a mathematical expression that looks something like this. dv dt is equal to the apparent forces plus all of the forces that can change, or the forces that act 90 degrees to the left or to the right of the object in question, plus all the forces that act in the same direction as the object in question. And that is all equal to the sum of all the mass normalized forces. And so we showed that this term right here just simply represents all the apparent forces. And then now we can start plugging in stuff for instance, the pressure gradient force, which is something we derived in the previous segment. And again, that's what this looks like in natural coordinates. And if you go through and work out all the ugly algebra and math, you can show that this is in fact equal to, you can arrive at an expression that looks something like this, where you have dv dt t hat on the left-hand side is equal to all of this other stuff on the right-hand side. And this looks pretty looks kind of not fun to look at from a mathematical standpoint, because you have all these t hats and you have all these n hats in here. But what you can do, just like you can with a Cartesian coordinate system, all the stuff that appears in front of the unit vectors must be equivalent. So if all the stuff that appears in front of the t hat unit vector on the left-hand side of the equal sign must equal to everything on the other side of the equal sign that also has a t hat vector next to it. And similarly, if everything that has an n hat unit vector next to it must be equal to everything on the other side of the equation that has an n hat unit vector in it. So in the case of resolving the components in the t hat direction, we get that the t component is equal to this dv dt is just equal to minus d phi ds, which you remember this term represents the change in forward speed of an air parcel, and you remember that this term is a pressure gradient force that acts in the same direction as an air parcel. Now on the left-hand side of this equation, we don't have any sort of n hat term. So that means that we just have a zero n hat on the left-hand side of this equation. So that means all of these components on the right-hand side that have an n hat term in them, all of those must add together to equal 0. So we get that 0 is equal to negative v squared over r minus fv minus d phi dn. So if none of this stuff up here makes sense, just make sure that you focus on this. This is basically the end result you get from doing all the fancy and lovely algebra. I use those terms a bit facetiously, but this is what you get after doing all the algebra. And the main thing that we want to focus on is what these two equations physically represent. And this actually is a lot simpler to work with than the equations of motion we had in Cartesian space. So even though it seems like we unnecessarily complicate everything, this is actually a much simpler form of our Newton's second law for equations of motion to actually be working with. But the main thing that I want you to focus on is these two terms and what they physically represent. And we're actually going to spend a little bit of time talking about what those two terms physically represent. So let's first focus on this t hat component. So I kind of said this earlier. The change in forward speed of an air parcel, the only thing that can change that is the pressure gradient force acting in the same direction as the air parcel's motion. And the n hat component, which represents sort of the change in the air parcel's direction, there are three forces that can sort of change that. That is the centrifugal force, minus v squared over r, the Coriolis force, this lowest case f being the Coriolis parameter times v, and then the pressure gradient force acting 90 degrees to the left or to the right of an object's motion. So the only thing that can change the forward speed of an air parcel is a pressure gradient force that's acting in the same direction as the air parcel. And we'll see an illustration of what exactly I mean by that a little bit later on. Whereas, just like before, remember I mentioned centrifugal and Coriolis force, they only change the direction of an air parcel. They don't actually change the forward speed of an air parcel. But the same is also true for pressure gradient forces acting perpendicular to an air parcel's motion. That is, if there's a pressure gradient force acting to your left, that's just going to change your direction. It's not going to actually change your forward speed. And the same thing also applies if you have a pressure gradient force acting to your right. That's going to change your direction of motion. It's not going to actually change your forward speed. So let's take a look at this in a little bit more detail. So let's say we have a pressure field that looks something like this. So you'll see that here I've got an air parcel that's moving from south to north. And you can see as I'm going from south to north, you see if I had a pressure gradient, a pressure gradient force, it would be pointing from south to north. So that pressure gradient force is pointing in the same direction as the air parcel's motion, which means this air parcel is going to want to increase its forward speed as it goes from south to north, because the pressure gradient force is acting in the same direction as the air parcel. And if this picture were reversed, if my air parcel were going from north to south, it would be slowing down the air parcel, it would be decelerating it, as the pressure gradient, as again that pressure gradient force is acting in the same direction as the air parcel's motion. So here, as this air parcel moves from south to north, it's encountering a pressure gradient force that is acting in the same direction as its direction of motion, and because of that, it is going to change its forward speed. Now let's take a look at the in-hat component of this, the in-hat component of this natural coordinates equation that we just derived. So let's consider a flow pattern that involves an air parcel that's circulating around, say, a cyclone. So at this point along the cyclone, down here at the bottom, the pressure gradient force points 90 degrees to the left, so it points toward the center of the low. And what that does is that serves to change the direction of the air parcel's motion, but it doesn't actually change the forward speed. In fact, under this highly idealized circumstance, all the air parcel just wants to do is it just wants to rotate around in a nice circular path. Even though there's a pressure gradient force acting on it all times, that pressure gradient force is not acting in the same direction as its forward motion, so it doesn't actually change the forward speed of the air parcel, it only changes the direction of the air parcel. And same thing for this northern point. Here my direction motion is initially pointing this way, and my pressure gradient force also points inward, it points to the left of the velocity vector. And that will only, under this highly idealized circumstance, that's only going to change the direction of the velocity vector. It's not going to actually change the magnitude or the forward speed of the air parcel in question. So a pressure gradient force acting in the same direction as an air parcel, that will change the forward speed. But if the pressure gradient force is only acting perpendicular to the velocity vector, then that's not going to change the forward speed. It's only going to change the direction of motion. So that's going to do it for this segment. And in the next segment, we'll take a look at some force balances and how those actually work out mathematically in our natural coordinate system. So with that, I will see you all in the next segment.